Hello everyone. Today we are going to discuss an important phenomena called resonance in an LCR circuit. So resonance, which you have studied in mechanical case in class 11th, was when the amplitude or the amplitude of oscillation becomes maximum, then we say that it is a case of resonance. So when it happens, if you remember the case of a swing. So if this is a swing, it has some natural frequency and someone which is the external force is giving it a frequency. So if the natural frequency is equal to frequency of applied force, then this swing oscillates with maximum amplitude, and this is called resonance. But when we are talking about LCR circuit, then this is not a mechanical case, so we can't see it with the eyes. Here the resonance will be observed in the form of maximum current, and this will be the case when the capacitive reactance is equal to inductive reactance. We will discuss about that using the mathematical formula only. So at resonance, the current in the circuit is maximum. So if you recall the formula for the current, this was this. We can write it like this also, where Z is the impedance, which is equal to this denominator. So the current will be maximum. This can also be written it like this also. So I is maximum if Z is minimum. Now what is the formula for Z? Z is under root of R square plus XL minus XC whole square. Now this will be minimum if some quantity somehow becomes 0. We know that LCR all are here. Then if this quantity is 0, then we can say that the current is maximum. So for this to be minimum, XL must be equal to XC. So in that case, if XL is equal to XC, this will be R square plus 0 square, and this will be equal to R, right? So from these mathematical formulas, we can infer from here that conditions, what would be the condition for resonance? First thing will be the current is maximum. Second thing is XC must be equal to XL. So from here, if I write the formula for XC, this will be 1 by omega C and this will be omega L. And we are talking about resonance, so we can write the suffix R for the resonant frequency. So from here you can write down omega R square is equal to 1 upon LC. Therefore resonant frequency is equal to 1 by under root of LC. And we can also write 2 pi resonant frequency is equal to 1 by root LC. Therefore this frequency will be 1 by 2 pi under root of LC, right? So this is the second condition. Now for this we can write down the third condition on the basis of this discussion, that how much is the impedance? Impedance is equal to R, right? So that means circuit behaves as pure resistor, okay? And fourth point, if it works as a pure resistor, so maximum power loss, right? And fifth thing, power factor which is cos phi, and this is equal to r upon z, and in this case z is equal to r, so this will be r upon r is equal to 1. So power factor is 1. Now we come to another important concept, that is quality factor. So quality factor gives the sharpness of resonance. How can we say that the resonance is sharp? If we look at the graph between the current and the frequency, then we get this kind of graph, bell-shaped graph. Okay, so this value corresponds to the maximum current, and this value of frequency corresponds to the resonant frequency, and the side frequencies at which the current is 1 by root 2 times of I naught, that means IRMS. These frequencies are called sideband frequencies omega 1 and omega 2, and this complete width is called as band width. And this width can also be written as, this is 2 delta W written, because here this is considered delta W and this is also considered delta W. So 2 delta W is bandwidth, and this can also be written as, this is complete is omega 2, this is omega 1. So this bandwidth can also be written as omega 2 minus omega 1, right? And quality factor is written as resonant frequency upon bandwidth. So this gives me omega r upon omega 2 minus omega 1. This can also be written as omega r upon 2 delta omega, right? And also one more important relation here. Quality factor can also be written as potential drop across capacitor or inductor upon potential drop across resistor. So if I am writing potential drop across capacitor or inductor, so I can write IRMS XC upon IRMS R. So this can be solved like this. This is 1 by omega R C into R, and omega R is 1 by under root LC. So this can be written 1 upon under root of LC into CR, and therefore Q can be written as 1 by R, and this is C, this is under root LC. So this can be written root C into root C can be written like this, can be written as root C into root C. So this will be root C cancel. So this will be 1 by R under root of L upon C. Similarly, in other way we can find it, Q is equal to voltage drop across inductor. This can be written omega R L upon R. So this can be written 1 by under root of LC L upon R, and this can be written root L cancel. So this will be 1 by R under root of L upon C, same. Okay, so from here you can infer that Q is proportional to, inversely proportional to resistance. So if I want to have an idea about the value of resistances for 3 graphs which are given like this, so in which case the sharpness is more, in the topmost graph the sharpness is more, and the sharpness decreases as we go here. So if this sharpness is more, that means this resistance must be less. So low resistance, more sharpness. means R1 is less than R2 is less than R3. So this was all about the quality factor, resonance, and the variation of quality factor with resistance. And conditions of resonance are very important from the numericals point of view. I hope you understood everything. That's all for now. Have a great day.